Hello and welcome to this math video explaining how to find the nth derivative of the error function. So this is what the error function is. It's the antiderivative of this exponent function. It can't be found using common functions like cosine, exponential or tangent. So a new function must be created to find it using power series. It's important because it's used in statistics and models statistics in the real world fairly accurately. So we'll start from this function and rewrite it using word notation so that the square term doesn't get too small. And this is the first derivative of this function, and we can express it right away in terms of itself. We'll set this blue e to be equal to this function. So this is the first derivative of e. And this is its second derivative. It already has two terms added together, so that this is what will happen to the higher derivatives. And this is its third derivative. It has a very similar behaviour to the derivatives of tangent, inverse cosine and inverse tangent. Notice that the variable e is never raised to a power other than 1. We can use this to simplify our calculations. We'll set this variable w to be a particular term that we'll find in any of our derivative expressions. E won't be raised to a power. Then this will be the next derivative of w, being the sum of two terms. This is similar to the derivatives of other functions that we've created computer functions to find derivative tables for. So this is the data structure that we'll be using, a list of pointers pointing to the start of expressions in a second array. We won't be storing e in this array, because we know that any term will have it as a factor raised to the power of 1 only, but I've included it here to avoid confusion. We'll only be storing the coefficient and the power that x will be raised to. And this is the algorithm for finding the next derivative. We'll calculate the next derivative from the previous one and place it into the construction array. Then we'll gather like terms together. These are circled in pink. Then we'll eliminate all of the zero terms circled in blue. Then we'll place it back into the table. Now to write some code to do all of these things. We'll create this function to get the next derivative from the previous one. We'll get the start and end points of the derivative that we're working on. Then we'll create a loop to look at every term in this derivative expression. Then we'll get all of the constants associated with each particular term. There's only 2 this time. Then we'll calculate the constants for the next 2 terms of the next derivative that we're calculating. We'll then place these constants into the construction array. Then we'll store the length of this derivative that's in the construction array. So we've got to simplify this expression before we can place it back into the table of derivatives. We'll have to gather like terms together first. We'll make a loop to look at every term in the expression and get the power of x in this term, which is stored in m. We'll make another loop to look at every term ahead of it. And if its coefficient isn't 0, then we'll look at the power that x in this term is raised to. And if the two x's are raised to the same power, we can add the coefficients together. And we'll set the coefficient of the other term to be 0, so that it may be deleted by the 0 eliminate function. So now we've got to eliminate all of the 0 terms in this expression. We'll do this by having 2 index variables in the same loop, so that one will lag the other, only writing the term when its coefficient isn't equal to 0. We'll make up a loop to do this. We'll get the coefficient of this particular term in the loop and get the magnitude of it. And if its magnitude is large enough, it means that it isn't equal to 0 enough. So we'll write the term in another location and increment the lagging variable, having the effect of deleting all of the 0 terms. The length of this expression will be shorter, so we'd have to set the new length of this expression here. This function copies the new derivative that we've found from the construction array and into the table. So now we have to put all of this together into a function to create the table of derivatives. We'll set the first element of the table here to start it off, since it is an iterative process. We'll also set the number of derivatives found here. The the program needs to use this variable. We'll make a loop to find the rest of the derivatives. We'll call the function to find the next derivative from the last one. That's why we need the first one. We'll call these two functions to simplify the expression. We'll set the start and end pointers for this next derivative. Then we'll copy this newly found derivative into the table of derivatives and increment the number of derivatives found so far. This is the function used to test the derivative table using numerical differentiation. We'll write out a message that we've started the test. We'll display an error if we're passing a parameter that isn't correct for this function. We'll get the locations in the array for two derivatives that are next to each other in the table. One should be the derivative of the other. We'll make a loop to check these derivatives for n1 values of input variable. So we'll get a good range of input variable. I've called it R for random number. It won't give nice numerical results if it's too close to 0. So we'll get two more values that are extremely close to R for numerical differentiation and calculate the value of E for them. We'll calculate the value of the function for the next derivative up the table. So we'll get the values of the derivative just before this other one in the table. And we'll get the derivative of this expression using numerical differentiation here. This value should equal the last one. We'll get the difference between these two values, both the absolute and relative differences, and get the smallest difference. And if they aren't equal to each other enough, then we'll display an error with lots of variable values that can help us to debug the code. We'll display a message that we've finished testing the derivative table here. And this function puts all of this together, firstly making the table, then testing it. We'll test each derivative 1,000 times, which goes very fast. Then we'll print out the table. This function prints out the table as constants. This function prints out the table as algebraic expressions. The variable e is written at the end of each term here. And here is the table of derivatives. It has similar behavior to the other functions. The number of terms climbs as half the number of which derivative it is. The coefficients get larger, but not too large. You could easily store such a table to the millionth derivative, but it would be harder to test. The polynomials in this table are naturally sorted and don't need to be sorted by an extra function. They can be stored as polynomial types with the position in the array corresponding to the power of x. This takes the same amount of memory though, and isn't necessary here. So I hope that you have found this video to be helpful, interesting, insightful, and possibly entertaining. Please click like and subscribe if you did. Feel free to share this video. Please leave some helpful thoughts and ideas in the comments. And thanks a lot for watching.